All right, let's go for it. So we're going to talk about crystal formation, sacred geometry, which it actually is. So we're looking at solids, and what is special about solids is they make this regular crystal pattern. And why that's important, since it's a regular pattern, it has geometry, and so we're going to do math with it. So to start with, I decided to go with the overhead because I did start with the whiteboard, and my ability to draw circles was lacking. We'll just say that. It's not my forte. I can draw zigzags for fatty acids and stuff, but the idea is these blue balls or brown balls, they're atoms, and the atoms pack together in different ways depending on the element. And so with this first one showing, which is really impractical, most things don't do it. They call this here actually the primitive way. And if you think of them instead of like atoms, think of them as apples and oranges. Are you guys doing my healthy challenge? I know Carolina told me she listened to my video and found it. And so she's doing the challenge of eating three pieces of fruit a day. So take me up on the challenge. Be inspired, whatever it is. You can watch the video and pick what you want. But oranges wouldn't stack this way, but something does. I can't remember what it was. It was something like iridium or something. So if it's stacked this way, we call it simple cubic. And the idea here with simple cubic, I'll try my best to draw these, is if you had this whole array in 3 dimensions, continuing on, thousands of atoms going up and down and left and right, that this is our simplest one. And so if we went from the center of each atom to the center of each of the next atoms, we get a cube. And that's what they're trying to show here in 3 dimensions. And so what happens is what's inside this part of the cube is each one of these atoms. So just the corner of each atom. And in fact, each of these atoms is part of 8 different cells. So there would be one next to it right here, and it would be part of that, and it'd be part of the one above it, and the one here, and the ones in front of it or behind it. So every corner, you actually only have 1/8 of an atom per corner. And I think I should write it down here, that in a corner, you actually only have 1/8 of an atom per corner. Now, if we're talking about faces, I'll try and draw this. This would be if the atoms are stacking more like this, which seems more practical if you're talking apples and oranges. Of course, you would put the lowest row on first, but what happens is they don't actually touch along the edge here. So we'd have one up here, we'd have another one here, and you don't have to try and draw them. And on the lab, it tells you to use quarters and nickels, and I should have gone for that. But this is our idea, and it keeps stacking on and on and on for quite a long time. And so what happens is if we keep going on and on and on, and even above, right, and below, that you keep getting this repeating cell. And this is what it would look like in just 2 dimensions. And what it is these atoms are touching along this diagonal, which is along the face. And so a face position is this atom here. And what happens, I'm trying to think, I'm going to flip our paper over so you can do it too, is this is what I was trying to draw. And so they cut it. And so here you can see in this picture that this is a cube. It's a repeating cube that keeps going on, depending how the atoms pack. So this would be example here. And when we read my story, which I will do at the end, it actually talks about, you can actually Google and see what atoms pack which way, which lots of information. But these are the corners. And so there's only 1/8 of an atom in this cube. There'd be 1/8, that atom is a whole atom, but it's in 8 different cubes. So this face position, if we cut it, half of the atom is in this cube that we're talking about, and half of it's in the cube next to it. All right. This is always the awkwardest lecture, and usually this is at the end and everybody's tired and they just go, okay, Just give me the information. So you have half of an atom per face. Now the center is easy. That's this brown ball here in this picture. That brown ball is completely in the cell. So you have a full atom. So one full, total, complete atom. And sometimes you have multiple ones in the center. What's showing on this picture is they're kind of trying to, it would be cut in half because half of that cell would be in the one in front of it, or to the left or to the right. Now the edge position, I'm trying to think if I have a good one that shows the edge. Probably not. An edge position is kind of what they're trying. No, that's a face. That's side-centered. You're going to have to take my word for it on this one. So for an edge position, we get to it on the last page. 1/4 of an atom per edge. So an edge would be like here, that you have the atom here in that cell. And so this edge is part of 4 cubes. One of the easiest ways, if you're really having trouble with this and you want to try and get it, is go and collect some dice. You probably all, because you're at home, you probably have some dice. And if you stack the dice up, the edge would touch, this edge would touch 4 dice. I actually have dice in the next room. We can do it. Hold on. You can write down that information or draw your picture. And I'm back. And you're like, where'd she go? Why didn't she just pause it? Because that would mean you knew what I was doing. We could write words with these. All right. Lendler. All right, anyway, it doesn't matter. So if we were talking about this edge along the L, that edge, these were actually one cell. So like the face, you only ever have 2 faces touching. So an atom would be half in the L and half in the N. If we had a corner, so this corner here is part of these 4, but then it would be part of the 4 on top. I didn't grab enough dice because my hands are small. So if we're talking about an edge, so let's say this edge at the bottom of the L, it would be part of that cell. These would actually merge and be the same, so it's still the same edge there, and be part of that one and part of that one. So if we had, we can take it this way. If we had an atom in along that edge, it would be part of 4 edges. So only 1/4 would be in each one. So these are kind of the numbers that we'll be working with. And you can go, what is she talking about? And you can Google it. They probably can do stuff with cool 3-dimensional stuff. All right, so let's finish the math here. So in a corner, you have 1/8 of an atom per corner, and there are 8 corners in a cube. So the 4 on top and the 4 on the bottom times 8 corners. So when an atom is said to be in a corner position, it means you have 1 atom. I know, why do we go through all this math just to get back to 1 atom? But this is where the math comes from, that 1/8 of an atom, and you have 8 corners. All right, how many faces are on a cube? Well, I have a G, an N, an M, an N, another N, another A. All right, or you could just do numbers where you have 6 corners. I'm sorry, 6 faces. So half an atom per face times 6 faces is 3 atoms. The center per face. This was per corner. You always end up with 1, and that's how you would show how you got to that. And the center, however many is in the center, you get 1. And when you do the homework, the whole first page of the homework walks through these different ideas, and this is the basic math. Sometimes they get 2 in the center, and so this will come out as 2, but if it's in the center, it's a full. And if something's along the edge, how many edges are on a cube? Oh, there's 4. And then there's 4 at the bottom and 4 along the side. So we have 12 edges. So there would be 1/4 times 12 is, we're back to that magic 3 atoms per cell. 3 edge atoms. That's how I should have written this. So 3 edge atoms per cell. And this should say 3 face atoms per cell. And this should say 3 corner atoms per cell. All right, hard to believe that I'm like this when I was in 10th grade, a genius in geography, but that's the idea. There are all these different shapes. We're going to only do cubes. And the reason we're only going to do cubes is when you do a cube, the volume of a cube is just a cubed. So A is the side. We're not going to have to do rhomboids where you have to figure out the side is a different length than that side, or hexagonal things and stuff like that. We're just going to look at 3 basic types of cubes, and we're going to run into these positions. All right, so let's just do it. Face-centered and body-centered. So I'm going to show you where the math comes from, and then we'll just do the math, and that's what your lab is for this week, is a lot of number crunching. So normally you would find density in lab, so the gnomes did it for you, and you'll just read the graduated cylinders and figure out your math, and hopefully the gnomes are really good, and they're very precise. So those of you who like sig figs, you're going to use a lot of them. All right, how many atoms are in a face-centered? I'm going to show you how you show your work for this. That in a face-centered, you have 1/8 of an atom per center. I'm sorry, per corner. There's no center here. Times 8 corners. And then you have 1/2 an atom per face times your 6 faces. All right, so we get 1 plus 3. So this is 4 atoms. Now, there is a shortcut way of saying face-centered. Instead of writing this out every time, you'll just see me say FCC. So we just say there's 4 atoms per FCC. Sometimes I ask to see how you got to that. So like on the homework, study set 3, the first page, you get to show this. And then when we get to the big math questions, if we're going to get to on the next page, you just say, okay, it's FCC, there's 4 atoms. And then what's the relationship in an FCC between the edge, so this would be the edge, and the volume? I'm sorry, and the radius of the atom. So we have this gap space here. So we can't just measure along the edge. Where they touch is if we look this diagonal here, just a little better with that, the atoms touch. And we actually have 4 radiuses along what I'm going to call the face diagonal. Okay, I don't know how you spell diagonal. So you're seeing my writing spelling abilities here. So radius is only halfway right across the whole circle. So this is 2 radiuses because we go the whole diameter. This is 1 radius, and this is 1 radius. So there's 4 radiuses equals the face diagonal. Right, this is A, and this up here, this length is A. And I'll call the face diagonal F. So you never have to repeat this math, but I think it's helpful for a handful of you to see where my magic equation is going to come from. And some of you are going to be like, okay, that's great. Awesome. So remember the Pythagorean theorem, a squared plus b squared equals c squared? He plagiarized that, by the way. He didn't not actually come up with it, but he gets all the credit. He was actually lived a long life, I think 108, and a very vital life. He lived in an area, you know, they were whole food, plant-based back then. They didn't have all this processed crap that's causing all the problems. So we don't, our A and B are actually the same. So we're just going to say a squared plus a squared equals c squared. And then C is the hypotenuse. Remember that word from way back? Is that bringing back great memories? It is for me. I had a twin brother, and we were known as the geometry twins because we were apparently really good at geometry. I didn't know I was good at it because I had a twin brother who was also good. So I just thought everybody was. So this is the F. I'm just going to call this F along there. So a squared plus a squared equals f squared. So we would have 2a squared if we combine these two equal f squared. And why that's important is f was equal to 4 radiuses. So f, instead of writing f, let's write it as 4r squared. Let's get rid of those squares because we don't care about the relationship in the squared world. We care about it in just our linear world. So if we square root both sides, but we're going to ignore him now, we would get the square root of just 2 times A is the length of an edge, equals the 4 and the r are both squared. So when we square root it, we're just left with 4r. So for those of you who are scratching your head, you can always hit that rewind on YouTube, or you can just go, okay, for FCC, it's always the square root of 2 times A equals 4r. So we're going to do that with BCC. And really, this is the take-home message, is these two pieces are what you need to know about FCC. 4 atoms for FCC, square root of 2 times A equals 4r is FCC. You're going to have your notes for doing your lab, and yes, this will be on exam 2. This is why I didn't post it before exam 1, because we didn't need this in our heads. All right, so for BCC, it's easier. You have your corner, right, 1/8 of an atom times your 8 corners. And then you have one whole piece in the very center, plus 1 in the center. So we're going to get 2 atoms per BCC, bodied centered. So in a bodied centered, they pack these how they pack. One of them is called a tetrahedral hole. This would be more probably how oranges and apples would pack. Anyway, we get 2 atoms per BCC. We're going to do the relationship, and this one's pretty funky. They don't touch along the edge, and they also don't touch along the face. Where the atoms touch is if we go from this corner here to this corner back here. All right. So we're going to do the real Pythagorean theorem, because Pythagoras was actually really good. So the real Pythagorean theorem was the length squared plus the width squared plus the height squared of a cube, which is really all a's, a squared plus a squared plus a squared, right? Because we're a cube, or 3a squared, is equal to this diagonal squared from one catacorner to the other catacorner. So I'm going to call that the body diagonal, or b squared, or you can call it d squared. It doesn't really matter, because we're going to get rid of that piece in a minute. And what it is along the body diagonal, you have 4 radiuses. So again, we go across this whole circle, and then we go through these 2 partial circles, which are 4 radiuses total. So we get 3a squared equals b squared, which is going to be 4r, and that 4r together will be squared. We square root both sides. Just rewind me. We get the square root of 3 times a equals 4r. It's probably good that I'm not doing this in front of people, because there's always lots of questions. This is the take-home message for BCC. And it was actually, everybody always got this in the class could remember it, or I'll just tell you real quick. In FCC, you only go along 2 faces, 2 edges to get the diagonal. In BCC, it's 3-dimensional. So this is really a 2-dimensional, and this is 3-dimensional. So that's why it's the square root of 2. This is square root of 3. The a is not inside the square root. And again, a is how I talk about an edge. I think your book might use an L, and I don't like the L because then people confuse the L with a 1. So I use the A. All right, so let's do the real math. So where it's going to is this page, is we're going to do a bunch of calculations. And there are always 4 variables when we're doing math with solids. So we're first going to do just different types of metals. So like aluminum, vanadium, and a mystery metal. So there's always 4 variables. Is it BCC or FCC? And I actually always give you that piece of information. Otherwise, you have to solve the problem twice and see which one it works out for, which is really fun to do. And I used to do it my first few years. And I used to do like the other ones, and it's really fun. But in all honesty, a couple of you do it and the rest of you just copy. So the other 3 variables are the radius, so r, the the metal type. So the radius, the metal type is going to be grams per mole. So, oh, periodic table. If you don't have your periodic table, definitely go get it. But if we're going to talk like here about aluminum, that's going to be our piece of information. And so our starting point is going to be that wonderful number on the periodic table for aluminum. That's 26.98 grams per mole. All right. And the other piece of information is density. I'm always going to give you the BCC or FCC. So on this one, we know it's aluminum and we know the radius. Our question is, what's the density? And for those of you who are new to me, in my notes, I always have here in parentheses the answer. I have a question mark there because I actually know the answer, and the answer I had there was wrong because I did the math before I started this video. I learned. All right, so on this one, the question we're trying to do is we're calculating the density. On the next one, we're going to calculate the radius. And the last one, we're going to figure out what the element is. We're working with metals here because it has to be a solid. All right, so let's go through the math. So if you know what it is, like aluminum or vanadium, start there. That is the easiest place to start. And our first step is we want to get to atoms. Let's see, does anybody remember how to change moles to atoms? I'm pretty sure all of you remember this very special number. So I am perfectly okay with you abbreviating it like that. Or you can write it in. I'm just going to write underneath to remind you. You shall be saying in unison 6.022 times 10 to the 23. You do not have to write that number out, but you can. You can just use this notation. It's a capital N and then a subscript capital A for Avogadro. All right, that cancels our moles out. And where we're going with this is if this is FCC, if you remember from our previous page, FCC is 4 atoms per FCC, and the square root of 2 times A equals 4 radiuses. So there are 4 atoms per 1 FCC. All right, this will give us our mass per FCC. We're not done. Density, if you remember, is mass per cubic centimeter or mass per volume. So this is our mass. And then we're going to figure out our volume. And I did try this on the whiteboard and just, it's going to work better on this. And then you can do a lot of number crunching. Your study set is really short and it has the answer key. So you can do that. Your worksheet is all organic chemistry practice, just 2 pages. And so that's what's due on Tuesday. It's really not that bad. And then the lab is 4 pages of these number crunching. All right, so I punched this in. You can pause me and punch it in, or you can say, oh, I just want to know what the number is. 1.792 e to the negative 22. We are going to get crazy exponents. The exponents are really important. So you can either write it as capital E, or you can say times 10 to the negative 22. All right, you can break this into steps. I'm going to do this one as one big step. But you can break it like that. That's my mass. I'm labeling. That's my mass. And now to find the volume. The volume, since we're working with a cube, is always equal to A cubed. So it's FCC. So we know this little formula. That we'll just write here. This was my step 1. Here we're going to do my step 2. And then I'll also show you how to do it in one step. There's probably 2 of you, maybe 3 of you, who are going to be like, yeah, I'm a one-step type of person. And the other 20, 21 of you are going to be like, I'm going to break it into steps. That what we know about FCC is 4 radiuses equal the square root of 2 times A. Because that's in your notes, nicely highlighted or somehow in color. All right. We want A because we can then cube A. So we really have 4 radiuses divided by the square root of 2 equals A. And then if we cube that, we can just plug it right in. So you can break it into steps, or you can do it all in one step. So again, I'm going to do it in one step. So I would just say 4 over the square root of 2. I'm sorry, 4 over the square root of 2 times r. And r was up here, was 1.432. And then it had the A with the halo. Does anybody remember what that was? That's an angstrom. And it's a very special unit that chemists use because it's the radius of different atoms. All right, so 1 angstrom, whether you remember it or not, it's going to be here, is 10 to the negative 10th meters. Or you can say 1 meter is 10 to the positive 10th angstroms. And then 1 meter is 100 centimeters. Density in our world, in chemistry world, you're going to be asked to solve for density in grams per cubic centimeter. Because in lab, if we were really doing this, you would be measuring it with graduated cylinders in milliliters. And if you remember, a milliliter is a cubic centimeter. Solids are normally thought about in cubic centimeters because they're three-dimensional, right? And then, if you want, you can break this into a step. This would be that was my radius is 1.432. If you punch it in, e to the negative 8th, I don't need, that's centimeters. It is easier to switch it there than after you cube it. Just a hint for you. And I'll break it better into steps in the next one. All right, you would find this number, and then you would cube it. So some of you are going to want to first figure out what this whole thing is, which I apparently did. You don't need to, but I'm giving a partway step in case you're not going to get my final answer. You can maybe see where you're messing up. Hopefully you can see that. 1.432 e to the negative 8th. I wanted to write that also because that is something you're going to find whenever you do the radius or the length of a side. You're going to end up with your centimeters as 10 to the negative 8th. And that's how you'll know that you're punching these in right. That's just the size of atoms is 10 to the negative 8th centimeters. Anyway, once we punch this whole thing in, you should get, for the cubic centimeter part, 6.645 e to the negative 23rd cubic centimeters. And that would technically be per unit cell. We would then take our grams from up here and divide by that piece, and you should get 2.697. So in lecture, this is where some of you are ready to move on, and some of you are going to want to hit the pause and go and do that to make sure you can get the numbers. I'm going to move on to the next one, which is vanadium. V, I miss her. Vanadium is, right, handy dandy periodic table, 50.94 grams per mole. If you know what it is, this is a great first step. So I'm going to number my steps. This was step 1. Like up here, if you broke it into steps, you would label this was my step 1, this was my step 2, this was my step 3, and then I brought them together. Here I am going to break it into steps, but you can always do this in one setup. Just make sure your units are labeled, and again, there's usually 2 people who their brain thinks that way and they like that one setup. All right, so Avogadro's number of atoms, and this one was BCC. So 2 atoms per BCC. Oh, but we're not going to stop yet because we know one piece of information here, which is density. So my atoms cancel, my moles cancel. I can actually bring density in here. And I can convert this all the way to the volume. So that's what my first step was. So this V here was for vanadium per volume. And you would punch this in your calculator and we get 2.77. If you want to respect sig figs, you can keep more sig figs, and then at the end you can respect your sig figs. And this is cubic centimeters. My grams canceled per unit cell. You can just say cubic centimeters. Technically the thing is per unit cell. This is the volume. All right, so that's my step 1. Step 2 is volume equals a cubed. So if you take the cube root of the volume, so we take our number 2.77 e to negative 23 cubic centimeters, and we take it, you can either write it as the cube root, you just know how to write a cube root, or you just take it to the 1/3 power. That will equal a, which is, did this before, 3.03 or 3.025 e to the negative 8. Some people like to keep 4 sig figs and extra sig fig until the last step. Always drove me crazy, but it's not a big deal as long as you're, I wouldn't keep 8 sig figs because then you're going to be writing weird stuff down. All right, we're not done because we want radius. That's the length of a side. So our 3rd step, it's BCC. The relationship is square root of 3 times a equals 4 radiuses. So then you would show me your work. So notice I'm stating my formula as I'm using it. I can follow the steps, perhaps much better on this one than the one up there. So square root of 3 times, here I'm pulling this number down, 3.025 e to the negative 8. Notice I'm always showing my units. And then I'm going to divide by 4 because I want to pull my 4 over. And that will give me my radius, which will be 1.31 e to the negative 8 centimeters. And we did it. Check. Oh, I want it in picometers. Definitely want it in picometers. You guys know how to go to picometers? There's 100 centimeters in a meter, and pico is, nano is 9, pico is 12. So either 10 to the 12 picometers in a meter, or 1 picometer is 10 to the negative 12 meters. All right, one more, oh, and one more page. And, oh, we're in great shape. All right. So this one we're solving for what element? And that means the units we're solving for is grams per mole. That is what the question wants us to find. So we know it's BCC and we know the radius. So I did state if you know the element, start there. But we don't know the element. So we're basically going to work through this backwards. So I'm going to start with the radius. And I know it's BCC, so BCC, 4 radiuses equals the square root of 3 times a. So we're going to take 4 times our radius, 126 picometers, and divide by the square root of 3 to find a. And I already did this. So you can punch in your calculator. You can be like, okay, I trust her at this point. Because usually this was like almost 9 o'clock at night. You all trusted me. All right, that gets us to picometers. I'm going to change it to centimeters. Usually, it's easier to change it here because our next step, this is our step 1. Our next step is going to be that a cubed equals the volume. And once you go into cubic, it's easier to change to centimeters in 1 dimension than once you're in 3 dimensions. I've just seen that for students. So picometer, the way I think of it is pico means it's defined as 10 to the negative 12 meters. Or again, you can say 1 meter is 10 to the positive 12 picometers. I'll write that underneath. I don't care which way you do it, but you will at some point have to show your work. So you should feel comfortable with metric. If you're going into medical science, oh my gosh, that's what we use is these weird units like picometers and nanometers and stuff. So you want to be comfortable with them. So like I said, you can punch it in your calculator to see if you did it right. But does anybody remember the hint I gave? That it's to the negative 8th. So in centimeters, the radius will be 10 to the negative 8. All right, then we're going to cube it. So I do want you to show your steps if you're going to break it into steps, but show it really nicely. You can work it out in crazy dimensions, state your formula, then write your pieces. And I got 2.46 e to the negative 23rd, and that will be cubic centimeters. All right, so then step 3, we're going to pull our volume down to here. I actually just kept going when I did this before, which you could, but I would run into my mess there. And you can also, I apologize, you can also write your exponents like that. That's perfectly fine. Capital E, not little e, that would be a big mistake. All right, this is our cubic centimeters. And we do know the density up here. So 7.874 grams to 1 cubic centimeter. But don't break it into too many steps. Let's keep going here. We want grams, but we want grams per mole. And so the piece that will allow us to do this now is that factor label. And so this is where students had me, they had Dr. Whitman, Bernadette, that you should be pretty good at doing your unit conversions. One of the things you can think about, this is cubic centimeter per unit cell. It's the volume of 1 unit cell, which are so tiny, tinier than we actually can imagine. 10 to the negative 23rd, really? Like any of us could imagine that? I can't. The width of your hair is 10 to the negative 6. This is like, how could you even imagine this size? That's where the gnomes will help you. The gnomes are your friends. Befriend a gnome. All right, so let's just write this. It's cubic centimeters per BCC. That's our unit cell. And that's what that will always be told to you. The first one was FCC. So what we know is for every 1 BCC, there are 2 atoms. And the reason I'm going here is Avogadro's number of atoms is 1 mole. So my atoms cancel, my unit cell cancels. I am left with grams over moles. Grams per moles, you punch it in, and you will get, oh, we only have 3 sig figs because the radius was very vague, 58.4 grams per mole. And then you pull out your handy dandy periodic table, which I have a bright goldenrod yellow one here. And I go, oh, well, it's looking like nickel. My best guess is it's nickel. So I got this from the book, and the book said it was iron. And I'm wearing my irony shirt today because I found that ironic. In lab, we get close to things. The lab you're going to be doing, the gnome's got the numbers for you. So you're going to get things right on. You're going to then decide, I never want to do a lab again unless a gnome is my partner. But if this was a question, let's say like on your worksheet, I don't remember, I wrote your worksheet like 2 weeks ago. That would be your best guess, as it came out closest to nickel on the periodic table. All right, got one more page. Let's do it. And this is ionic solids. And this is where, so we're going to look at this one, which has lots of writing on it, just for the top part, because it has colors. There are different, if you notice, there's 2 different colors in these pictures, and that's because ionic compounds are made up of the cation and anion. They're actually usually made up of multiple things. But in this case, the cesium, they're telling you, is in the center, and then the corner. So it's a bodied centered cubic. But what's different from our previous problem in bodied centered, like this picture, the center is cesium, and then the corners here are chlorides. So that's one possibility. And the other possibility, so that would be for BCC, we're going to actually do the FCC possibility. And some of these you run into in your homework, and you just can try and figure out what would be the ratio. So the chlorides are all the corners and the faces. So this is not, this is sodium chloride. I'm sorry, that was calcium fluoride. That's chloride. So the greens are the chlorides, of course. And then they're on the face. And I'm going to go back to this picture, sorry. Is the sodiums fit into this spot here along the edge in here. These are all our little sodiums. I should have gotten a different color. So, and that's the bodied center. I can't believe I just did that. Okay, let's do that again. The sodiums will fit in here, in this space. So that would be another sodium fitting in there. And this would be the chloride here in the middle. So that's the idea of sodium chloride picture, and it actually shows the two down here. We're going to go through the math on the one that I have blank. I just didn't print it in color. So the reds would be the chlorides, and they're FCC, and the greens are the sodium. So they're squeezing in there. And so what we're going to see happens, and you can kind of see it in this picture, is when the sodium fits in there, do you guys see there's a gap? If you look on yours, there's actually a gap now between the chlorides. And we're going to go through the math to see why that happens. And we're going to do it with sodium bromide. On your lab, you do it with sodium chloride. It's the exact same calculations. You're just going to do different number crunchings. So we're going to do sodium bromide. And the question says, if bromide ions assume FCC, so how big is the space? So what we're doing, you can see me drawing these circles again. You can draw your circles. You can, you know, you get to do this on the lab for real. Look at that, I got better. All right, this is the FCC. You can draw three-dimensional. Some of you are going to shade. What we're trying to do is figure out the space. How much space from here to here? So the way we do this is we know there's 4 radiuses equals square root of 2 times A for face center. And what we know is along A is from this point to this point, you would have a radius here, and a space in between. So A is equal to 2 radiuses plus the space. So these are the 2 steps we're going to go through to calculate the space. And you can pause me and do it yourself. But we would just number crunch. So your radius of bromide, do it all in picometers. Don't change the centimeters. So we're going to have 4 times 196 picometers. This is all about bromide right now. Divided by the square root of 2 will equal A. And A, we find, when I did my math, was 554 picometers. So that's my step 1. And then my step 2, I took this A, my 554 picometers, and now I subtracted 2 radiuses of bromide. So 2 of these 196s, and I got 162 picometers. So that's the size of the space. That little space in here is 162 picometers. And so I said sodium doesn't fit. Sodium actually, when you try to put sodium in here, it's actually too big and it's going to push it apart. I say that in the next part. And you're like, oh no, Dr. Sherpa, sodium's 98. Why does 98 not fit in there? I swear. And pick on Carolina today. She's my top student because she sent me a lovely email and actually watched my video about your healthy change. And so that's how you can be my favorite student too. You can actually watch my video and then just determine that you're going to make a healthy change that's like really cool for the next month. And all right, and then you can make my day, and then I'm really happy. It's because that's the radius of sodium ion. And you have to be careful with this. I give you the numbers, but in case you like Google it, on the previous page, we were working with the metals. On this page, we're working with the ions, and they do have different radiuses. Sodium, this is just the radius. The whole sodium has to fit in, which means you need the full diameter, which this would be 196. And 196 is too big. So what happens when the sodium fits in there, if we're going to try and draw this, and you're going to get to draw this much nicer on your lab, is when the sodium fits in here. Sodium is smaller than the chlorides. So like for one, you can use a nickel. For the chlorides, you can use a nickel. And for the sodiums, you can use like a dime. And it's my chloride. So sorry, we're doing bromides. Bromide, bromide, bromide. And this fits in. And that's my sodium. That's my sodium, etc. You would continue. But what happens along our diagonal? Remember we were using this math up here, 4 radiuses equals the square root of 2a? It doesn't work anymore because that was all about that diagonal. Going back to that page. Oh, remember this page about the diagonal, and that's where all this came from? But they're no longer touching along the diagonal. That sodium went in there and pushed it apart. But I have great news for you. Really awesome news. The cow. I don't know where my cow is. Oh, the cow is like jumping with joy. And here he is. He wanted to be part of this. He says the math gets easier because the length of a side, A, is now just equal to 2 bromides. Radius is a bromide. This is how we would write it. You write it as 2R and then little subscript BR, plus 2 radiuses of sodium, because they're now touching along this edge. Same thing will work for chloride. So you have this bromide is just the radius. Then the whole way across the sodium is 2 radiuses of sodium. And then you have your other bromides. Remember, the corners, you only go halfway across. So you only do the radius. So to calculate volume, we just add these up. So this would be my step 1. So you take your 2 sodiums and your 2 bromides, and you'll get a number. And I did this math earlier. So you would show me your math. Keep it in picometers. That will make it easy. And then you can change it to cubic centimeters, to centimeters, and then to cubic centimeters. So my step 2 is up here. So once I have that, I would do A cubed equals my volume, and 2.03 times 10 to the negative 22, and you're going to show a unit. So where we're going with this is we're trying to find density. So you guys can look at the bottom of the page. To find density, we need grams per cubic centimeter. So we have our cubic centimeters, 2.03 e to the negative 22. We need to find the mass. So we're going to do that. So we have sodium bromide. I better write down what I'm doing or I'll do the wrong one again. So we have to talk about where the pieces are. So remember, the bromides are in the corners. On the lab, you'll show me, oh yeah, okay, so we have 4 bromides because they're in the corner in the face, because the bromides are in the FCC, even though they're not touching anymore. And the sodium must also be 4 sodiums. So how do we get 4 sodiums? Well, let me do the math here. So the sodiums come from, the sodiums are on the edges. So if you remember an edge, you have 1/4 of an atom times your 12 edges. We did that on the very first page. And that gives you only 3. So where's the 4th one come from? Oh, there's 1 in the center. And so when Joey was a baby, I decided with styrofoam balls, I got 2 different size styrofoam balls. I was going to make this 3-dimensional model for my students because I was on maternity leave and I was going back the day I was going to teach this. And no, it must have been Joey was 1. It's like a 1-month-old, he wouldn't have been able to do this. Yeah, and so I made it and it was beautiful and I colored the balls and you could see there was a hole in the middle where the one little ball fit. And then, you know, nature called. I went to the bathroom and I came out and Joey had taken my whole ball apart and was probably trying to stick something in his mouth because he was an infant. Anyway, so you have 4 of each. So to do the math, we have 4 sodiums times periodic table time 22.99 or something. Yes, 22.99 grams per mole. Plus we have 4 bromides and we would look at our periodic tables, 79.90 grams per mole. And then we would want to change that mole into Avogadro's number. And this is where we have to be careful on this unit. This is not an atom. It's not an ion, it's a compound. So they're called formula units. And that's up to you if you want to abbreviate it. I don't abbreviate it, but formula units of sodium bromide. You can just write Na of sodium bromide. That would be fine with me. And we're doing that because we got to Avogadro's number. Oh, we did. We got our moles canceled. We already did our 4. And these were 4 sodiums. We're good. We should be able to punch that in. And we get a number, which is, sorry, 6.834 times 10 to the negative 22 grams per unit cell. All right. You can always ask me during office hours. You're like, I don't understand that last step. This is for the last page of the lab. All right. So we bring this down 6.834 e to the negative 22, and we divide it by that number, and we get around 3.36 grams per cubic centimeter as our density, right? Mass over volume. And then we look on Google. This is what you guys are going to do. You're going to look on Google, and it tells you 3.21 is what Miss Google tells us. And we're close enough. We're close enough. Let's just go with it. So, hope you have a good day. Good luck with this. And, Tuesday, office hours, we're going to talk tonight because I'm going to start videotaping live. Either before or after office hours, whatever you guys tell me today, it'll be in the email I send out. And I'm gonna stop sharing. I can see my beautiful smile for a minute. And